In this video, we're going to go over significant figures. Now, significant figures are very important in science and in chemistry in particular. Significant figures of a measured quantity are defined as all of the digits that are known with certainty, so those that are indicated by the markings on a measuring device, and the first uncertain or estimated digit, which will be one digit past the smallest marking on the measuring device. So how can we kind of summarize that? Significant figures tell us how precise or good our measurement is. It's also a reflection of how good our measuring device is. So for example, down below, we have a ruler. Let's say that this is measuring in centimeters. And let's say we just want to measure the length of this gray block here. So of course we line the ruler up so that 0 is at one end, and then we get our length from the other end. So looking at where this lines up, so right about here. So that's about 1.3, right? So we know for certain that the block is 1.3 centimeters, but we also need to add an estimated digit because the block falls between two of the markings on our ruler. So our estimated digit, let's see, I'm going to call that, if I kind of divide this distance up into 10, I'm going to say that's around 6 out of 10. So 1.36. So again, we have our certain digits and our estimated digit. Oh, let me zoom out. There we go. So this reflects, again, how good the ruler is, or how precise the ruler is. And it also reflects how good our measurement is, right? So this will be true for any measuring device that we use. We want to make sure to include the certain digits and then an estimated digit, if possible. So let's look at some rules for significant figures, which sometimes we call sig figs for short. What numbers will be significant in a measured value and which numbers will be non-significant in a measured value? So for example, the last slide, we measured that block to be 1.36 centimeters. All of those numbers were non-zero digits. So the first rule for significant figures is that all non-zero digits are significant. So down below we have another example. Let's say we measured something to be 1,357 millimeters. Each of these digits are non-zero digits, so they're greater than 0. So they are significant, which means we have a total of 4 sig figs. Now, what if we do have a 0 in our number? Well, rule number 2 says that if the 0 is between non-zero digits, we call that an embedded or sandwiched 0, that will be considered significant. So down below we have the example of 405 grams. So because that 0 is in between two non-zero digits, it is significant. So that means that this measured value has 3 significant figures. The 4, the 0, and the 5 are all significant. Now, what if your 0 is in front of your number? So for example, let's say you have a very small number, a decimal. Are these zeros in front significant? Well, we call those leading zeros. So those are zeros that are at the beginning of a decimal number that's less than 1. And those are actually not significant. Now, the reason for that is they're really just placeholder numbers to represent how small our value is. Now, remember, we can express a really small number in scientific notation, right? So let's try to express this value, 0.000458, into scientific notation. Too many S words. All right, so I'm going to move this decimal over so that we can get a coefficient between 1 and 10 or equal to 1. All right, so I'm going to stop there because that will give me a coefficient of 4.58. And for my exponent, this is a small number, so my exponent will be negative. And I had to move my decimal 1, 2, 3, 4 times. So this will be -4 for my exponent. Okay, so if we look at the scientific notation of this value, we only have 3 numbers, right, in the coefficient. Those are all significant. So 3 sig figs. And remember, those leading zeros in our original value, our standard notation, those are just placeholders. So they are not significant. But the 4, the 5, and the 8 are all non-zero digits, so they are significant, which means we have 3 sig figs. So what I'm trying to say here is that, 1, leading zeros are not significant. But additionally, scientific notation is one way to express a value and its significant figures. So scientific notation only shows the significant digit. Or plural digits if you have multiple numbers. All right, so again, another useful reason to use scientific notation. It shows you how many significant figures you have. So now let's talk about zeros that come after non-zero numbers. Are those significant? So if a zero comes after a non-zero value, we call those trailing zeros. So those are zeros at the end of a number, and they're only significant if the number has a decimal point. So for example, let's say we measure something to be about 1,500 meters. Now, we're not entirely sure about that value, so we're not going to put a decimal after it. And because we didn't put a decimal after it, we're indicating to others that we're only sure of these first 2 digits, 1 and 5. So the 1,000 and the 500. So we only have 2 significant figures in this value. So it's not super precise, it's more of an estimation, right? But if we want to indicate that we are definitely positive that the length of something is 1,500 meters exactly, then we're going to put a decimal point and we're going to try to list as many zeros as we are sure of plus an estimated zero, right? So in the second written value, we have 1,500.00 meters. So that's going to tell the audience that this is a very precise number, and each of these digits are significant. So a decimal point makes all the difference. So if you don't have a decimal point, those trailing zeros are not significant. If you do have a decimal point, the trailing zeros are significant. Okay, so let's practice. And I have kind of a reminder up above of what leading zeros look like. buried zeros, and trailing zeros. Okay, so how many significant figures are in the following numbers? The first one, we have 4,097. Second value is 0.002803. Last value is 300. See if you can figure out how many sig figs each value has using the rules we just went over. And then once you unpause the video, we'll go over it together. All right, let's start with the first value, 4,097. So the 4, the 9, and the 7 are definitely significant because they're non-zero digits. But what about that 0? Is that significant? Yeah, so that 0 is in between two non-zero digits. It's a embedded 0 or a sandwich 0 or a buried 0, however you want to refer to it. So each of these digits are significant. So we have 4 sig figs. Now let's look at the second value. We have 0.002803. So we know that the 2, the 8, and the 3 are significant. But what about the 3 zeros in front? Are those significant? No, they are not. They are just placeholders to indicate how small the value is. And then what about the 0 that's in between 8 and 3? Is that significant? Yes, it's a sandwiched, embedded, buried 0, right? So only the last 4 are significant. And remember, you could even rewrite this value in scientific notation to express that those are the 4 significant digits. So this one would look like 2.803 times 10 to the negative third. So writing this in scientific notation tells us that the 2, 8, 0, and 3 are significant. Now, the last example, 300. How many significant figures do we have? Well, we do not have a decimal point, right? So we actually only have 1 sig fig. But what if we had written this as 300 with a decimal point at the very end? Then we would have 3 sig figs, right? So that decimal point makes all the difference. Now, sometimes with our measurements, we might have more digits than we really need to express the significant digits. And in that case, we'll need to round the number. So you might recall that when you round a number, if you have a 5 immediately after the number you're rounding, you round up. If you have something less than 5, then you round down, right? So first things first, let's say that you need to round 201.587 to 3 significant figures. So let's say that your instrument is only precise to those first 3 digits. So we need to check which value comes after the first 3 digits. Well, we have a 5, so that means we need to round up, right? So we're going to round this value to 202. And that will give us 3 sig figs. And we'll see more examples of this as we do more measurements in the future. But let's talk a little bit about adding and subtracting numbers, keeping in mind the significant figures, and then we'll also talk about multiplying and dividing. So for addition or subtraction, the rule is to stack all the numbers so that their decimal points are aligned. And then we want to limit the answer or round the answer to the value with the fewest decimal places. So that's going to give us our significant figures. So for example, let's say we need to add 56.789 and 102.2 and 1300.099. So we're going to line those up so that their decimal points are all aligned. And then we get our answer, which is 1459.088. However, notice that the number in the middle, 102.2, only goes to the first decimal place, the tenths place. So that means our final answer can only go to the tenths place. So what I like to do is I like to just draw a little line all the way through, and that's how I know where to cut off my answer. Part of the reason we have to do this with our values is we can only be as precise as our least precise instrument, right? So let's say we measured using 3 different rulers, and one ruler was just not very precise. And we had to add all of the measurements together. Well, we can't be more precise than our least precise instrument, so we have to limit our final value to that instrument's precision. So in this case, our actual final answer will be 1459.1 because the digit next to our last sig fig there is greater than 5. So this means that we have 5 sig figs, right? Each of those digits are non-zero. Now, what if we're multiplying or dividing values? So the rule for multiplication and division is to count the number of significant figures in each number and then limit the significant figures to the lowest count. So down below, let's say we measured the length of something to be 38.65 and we measured its width to be 105.93. And then we're trying to get the area of that object. So we're going to multiply those numbers together. So the first value has 4 sig figs because each of those digits is a non-zero digit. The second number has 5 sig figs. We do have a 0, but it's in between 2 non-zero digits, so it counts. So when we plug this into our calculator, the calculator will give back a value of 4,094.1945. However, we can only be as precise as our least precise measurement, right? So we need to reduce that big number down to 4 sig figs. So we're going to try to limit our value to these first 4 digits, but we also need to make sure to round. So the next digit over is a 1. And sometimes it's tempting, because the next digit is a 9, sometimes it's tempting to round the 1 up and then keep rounding. But just ignore these last 3, right? Just ignore those. So the next digit over is a 1, so that means we just keep the value the same. So we have 4,094. And that will give us our 4 sig figs. All right, so remember, with addition and subtraction, we're going to look at the decimal place. What is the smallest decimal place? That's what we're limiting our value to. But with multiplication and division, we're going to count sig figs for each value. And then we're going to limit our final answer to the smallest amount of sig figs. So let's practice. Let's calculate the following and then write the answer with the correct number of significant figures. So I'll let you work on this on your own first. You can pause the video, and then we'll work on it together when you unpause. All right, let's look at the first problem. So we're multiplying 0.0420 by 55.98. All right, so let's look at this first value. How many sig figs does it have? Well, this one's a little tricky, right? We do have leading zeros, which don't count as significant. But then we have what looks like a trailing zero. However, it does come after a decimal point. So this zero here is significant because it comes after a decimal point. All right, so we actually have 3 sig figs here. I'll just abbreviate that as SF. What about our second value? Well, they're all non-zero digits, so we have 4 sig figs. So when we calculate this or put this into our calculator, the calculator spits out a value of 2.35116, or something hopefully close to that. Now, since we're multiplying, we want to limit that answer to the lowest number of sig figs, which in this case is 3. So we're going to limit this to the first 3 digits. Now, do we need to round up? Nope. The next digit is a 1, which is less than 5. So our final answer is 2.35, which gives us 3 sig figs. Now, the next example is addition. Now remember, with addition and subtraction, we don't really care about how many sig figs each value has. We care more about the number of decimal places, right? So let's actually line up these numbers so that their decimal points are aligned. And again, I'm going to draw a little line just past the smallest decimal point, which is that 0.2. So when we plug this into our calculator, or if we do this by hand, let's see, we've got 2, 3, 9, 8, 5, 9, right? Okay, so 958.932. So we need to limit this value to the tenths place, so that 0.9. And do we need to round up? Nope, the next digit is a 3, so our final answer is 958.9. So this will actually give us 4 sig figs. All right. Now, the last example is a division example. We're dividing 30.2 by 23. So remember, in multiplication and division, we do care about the number of sig figs. So how many sig figs does the first value have? 3. We have an embedded 0, which counts, so that is 3. And what about the second value? Only 2 sig figs. So that means our final answer should only have 2 sig figs. Now, when we plug this into our calculator, it gives us 1.313 with a bunch of digits behind it. But again, we just want to limit this to 2 sig figs. And again, we don't have to round up because the next digit is a 1. So our final answer is 1.3. So that gives us 2 sig figs. All right. Now, one last thing before we end chapter 1. Typically, I know that many of the students who take Chem 121 are interested in field in healthcare. And in that field, you often have to calculate dosages for medication. Whether you're a nurse, pharmacist, doctor, you're going to come across this at some point. So remember, a dosage is the specific amount of medicine that is known to be therapeutic for an ailment in a patient of a certain size. And of course, it's a doctor's responsibility, or if a physician's assistant or a nurse's responsibility to prescribe the correct dosage for a patient. And it's a pharmacist's responsibility to provide that patient with the correct medicine at the dosage prescribed. So let's look at an example of, how to calculate the correct dosage for a patient. And we're going to use something called dimensional analysis. So this is going to give us some practice with dimensional analysis. So let's say a physician ordered 100 milligrams of Demerol for their patient. Demerol is available as 50 milligrams per tablet. How many tablets should the nurse administer? Now, looking at this, you can probably figure out right away the patient needs 2 tablets, right? But I want to show how we can set this up using dimensional analysis. So there's a couple different ways to do this. You can start with what you're given. So that's 100 milligrams of Demerol. And then you can multiply that by a conversion factor. So in this case, our conversion factor is 50 milligrams per tablet. And I'm going to put the unit I want in the numerator of my conversion factor. So 1 tablet over 50 milligrams. Now, I have seen some students use what are called train tracks to set this up. So I'll write that down below. And you might put a 1 over here under 100 milligrams. That works too. Whatever method you prefer is totally fine. But the idea with this setup is that you're then able to cancel your units and get the unit that you want. So for example, we have milligrams and milligrams in the numerator and the denominator, so we can cancel those out. We can see that below as well. Milligrams is on top and on bottom, so we can cancel them. And that way we're just left with tablets. So if we summarize this, we have 100 over 50 tablets. And down below, same thing, 100 over 50 tablets. So that'll give us 2 tablets. I ran out of room, but 2 tablets. There we go. So again, dimensional analysis involves setting up your given value with your conversion factor to cancel units and get the final unit that you need. So in this case, that was tablets, and we were canceling the unit of milligrams. So let's look at one more practice problem. Let's say the doctor's order is 1.2 grams of folic acid. Folic acid is available as 800 milligrams per tablet. How many tablets should be taken? So in this problem, we have the value that we're given, and we have our conversion factor. One thing I'm noticing though with our conversion factor, we have a different unit from the value that we're given. So we have milligrams, but the unit we were given was grams. So we might actually need to set up a second conversion factor. So let's see, we have our first conversion factor, 800 milligrams is equal to 1 tablet. But we also know that there's a certain amount of milligrams for every gram. So thinking back to our prefixes, how many milligrams are in 1 gram? So remember, milli was equal to 1/1000th. So if we have 1,000 milligrams, that would be equal to 1 gram. And I'll just write in parentheses, milli is equal to 1/1000th. Okay. So what we can do is we can now set up our dimensional analysis. I'll use a different marker color here. So I'm going to start with what we were given, 1.2 grams of folic acid. And we want to cancel the unit of grams, since that's what we're starting with, right? It looks like our second conversion factor has grams in it. So I'm going to put that 1 gram on the bottom, and I'm going to put 1,000 milligrams in the numerator. So in this step, we're canceling grams to get milligrams. And I can keep going, so I'm going to put my second conversion factor here. So I have milligrams right now, but I want to cancel it to get tablets. So I'm going to use that first conversion factor to cancel milligrams in the bottom, and I'll put 1 tablet in the top. All right, so now we've canceled milligrams, and we'll finally end up with tablets. So if we summarize this, we have 1.2 times 1,000 times 1 all over 1 times 800. And obviously we could leave out the ones because they just give us the same number back. But our final value, oh, I'm running out of room. We'll put it up here. Let's see, we end up with 1.5 tablets. And that's okay, because we could use a pill cutter, cut one of the pills in half, and administer it that way, right? So anyway, this was just to show you how to set up a problem using dimensional analysis so that we can cancel units and get the unit we want. And this is going to come up again in the future, so I just wanted to give you a preview of it, but we'll get plenty of practice with all of this. So that is the end of Chapter 1, and I will see you in the Chapter 2 videos.